those variables. And this assignment is used to check whether a given Boolean formula is satisfied. And compute the value of the collision. What's meant by this actually is that we give rules in a form syntactic. And whatever W, where this is a Boolean formula that contains the variables that represent our agents. Right? So containing variables in M, the set of agents. And this is some weight of this rule, which is just number. The idea is as follows. This formula says, for instance, I would say A and B, and I will give value 5. That would mean that every collision that contains both agents, A and B, will increase its value by 5. Or any collision that contains an agent B will increase its value by 2. So formally, the game is represented as an MC net that consists of a set of rules like this. There can be many of them, for instance, V1, W1, so on, VK, WK. And the valuation function, characteristic function, is then given by, so for each collision C, they would sum up over all the rules the weights of those rules where the assignment, the truth assignment that corresponds to our collision satisfies the corresponding formula. So let us denote it by phi I of E of C, right? So this is the characteristic vector of collision C that has ones for those agents who are members of the collisions and zeros for those agents who are not members of the collision. Right? And we would say that phi I of phi C equals 1 if and only if phi C satisfies phi I. So if we look at these two rules, A and B gives 5 and B gives 2, and we want to write down the values of all the coalitions when the game has only these two agents, A and B, then we would have that the value of the empty collision would be 0. The value of a singleton collision that contains agent A would be what?
0.
0 as well. Right, so we have two rules. None of them is satisfied, so we keep it at 0. The value of the singleton collision that contains agent B would be then 2, because one of the rules that has weight 2 is satisfied, so that's 2. And the value of the grand collision would be 7, right? Because both rules are satisfied, so we sum up their weights. So it's 5 plus 2, 7. So that's how the game is represented. We can also have negation of the variables, and we may have negative weights. In our rules. For instance, let us have A and B gives 5, B gives 2 as before, and also C gives 4, and B and not C gives minus 2. And now look at the game with 3 agents, A, B, and C. So what we would have in this case, as before, the value of the empty collision is 0, the value of the singleton with agent A is 0. Now what would be the value of collision containing agent B?
0.
0, right? So we have 2 for this rule, but we have minus 2 for this one because B is there alone, C is not there. So it's 2 minus 2, it's 0. A and B together give us 5 minus 2, right? B is there, C is not there. So that's 5 minus 2, but also plus 2 from B. So that's 5 plus 2 minus 2. So it's 5. A and C. This rule is satisfied, so that's 4. And B, C give us 4 for having C there, 2 for having B there, and that's it. Those two responses. So 4 plus 2 is 6. So you get the idea. Now, empty nets can represent any collisional game. because we may have this rule fully expressive, and just say for every collision we may have conjunctions, right? A and B and C there, give the value of that. So MC nets are fully expressive. And in fact, generalize the other presentations, such as the multi-issue. Remember what's that from last time? And the weighted graph representation. Now, what does it give us? When is it good? If we have a game which is given by the set of rules which are all conjunctions, then we may have Shapley value computed in linear time. So if a game is represented by an MC net limited to conjunctive patterns, then the Shapley value can be computed in polynomial time, but in polynomial time in the size of the input. So it depends how many rules I give. If the number of rules that we provide is exponential in the number of agents, then actually we didn't gain much. Now, why this is true? Because again, we can treat every rule as a separate game and then just use it utility. So we compute the Shapley value for each rule and then just sum up. So that would be linear, but linear in the input size. Checking the non-emptiness of a call. And membership in the core. Remain high. And why is that? That's because weighted graph games are a special case. And there, these two problems were hard when we may have negative weights. One of them was easy with positive weights, but with negative weights, they're generally hard. So that's the MC nets. Any questions on this? So the exercises that I'm going to give you is, given a set of rules, find the game. So that must be pretty easy. I will not ask you to prove any hardness have to keep in mind, given a particular domain and a particular application, whether you can use some of them to make your computation faster. Now let us just look at different cooperative games that come up from different multi-agent system applications. Many of them are defined on graphs. So one of them, we've seen it as a representation, but in fact it defines a particular game, the weighted graph game, where each edge in the graph has a weight, the agents are given by the nodes in the graph, and the value of the coalition is given by the sum of weights of all the edges which are contained in the given subgraph. So that's a particular game. Then there are other games defined on graphs. Many of them are monotone. Monotonicity, you remember, was that if we have a subset of a coalition, then its value is no greater than the value of the superset. And they come from different multi-agent system domains. One is spanning connectivity game. By the name you can actually guess what the game will be. So we have a graph with a set of vertices V and a set of edges E. It's connected and undirected. Do I have to explain what connected and undirected mean? And then a spanning connectivity game is a simple game, simple cooperative game. And where the set of agents is given by the set of edges in the graph, and the value of each coalition, which is just a subset of edges, you can guess by the name of the game. The value of the coalition will be, any thoughts? So that's a simple game. So the values of coalitions are either 1 or 0. So when would it be 1? It would be 1 if those edges contain a spanning tree. Do we know what a spanning tree is? So the value of the coalition would be 1 if and only if there exists some subset of edges E prime in our coalition such that E prime defines a spanning tree. So the graph T with the set of vertices given by all the vertices and the edges only from E prime is a spanning tree. Okay, what are the applications of this game? So one of them, you can think of a system administrator that has some limited resources and it needs to maintain links. So he needs to think how to allocate the resources so that it can connect between all the nodes in the graph, in the network. We can think about a spy network that comprises communication channels, and in order to intercept messages, it needs to think how to allocate its resources so that it connects between all the groups. It's social networks. We can also be interested in what links are the most crucial for connectivity between the members of the network, so that we can propagate information and so on. And how do we actually measure the criticality of a link in the graph in terms of connectivity? It can be, given the cooperative games, it will be measured by the power indices, either the Banzhaf index, do you remember what it is, or the Shapley bar. Right? So power indices would measure the ability of the level of connectivity of the given link. Okay. Now in these games, computing those power indices may not be necessarily easy, but Banzhaf index would be easy to compute in graphs which are bounded tree width. And I wonder if you know what bounded tree width is. Do you know what tree width is? That's a good thing to know in general. I'm not going to give you a formal definition, but just to explain. You have a graph. So you know that trees are nice graphs. Many optimization problems are easy on trees and generally hard on other graphs. Okay, so there is a way to take any graph, which is not necessarily a tree. So there may be many connections and cycles, and create a tree out of that graph by grouping. That's not necessarily the best way to do it, but you can group nodes so that that would define a cycle. I'm grouping nodes. I made 3 hypernodes so that I have links between them, and the graph with those hypernodes is a tree. Now the tree width of the original graph is the maximal size of this hypernode. So how many nodes I had to combine together so that the graph is a tree. So there is a way to find the optimal way of grouping the nodes. And if if the original graph is 3, its tree width obviously is 1. Right? Then other graphs may have higher tree width, and if tree width is not high, if it's bounded by a constant, then many optimization problems become easy. Not just those related to cooperative games. So that's a good thing to know for future, for any optimization you would have to do in networks. And let us move to another game. For example, actually this is what's still related to the to coalition formation. There is an optimization problem. Find the optimal coalition structure. So this is purely an optimization problem. It's not a game. So we have the set of nodes, and we have the characteristic function as a cooperative game, so it gives value to each coalition. We want to find the partition of the agents into coalitions so that the sum of coalitional values is maximized over all partitions. Another name of this problem is complete partition, if I'm not mistaken. And this problem is actually hard, but it can be solved in linear time if the graphs have bounded tree width. So always one more game on graphs. There are network flow games that we talked about in last semester. I think you remember those. So those are useful to model different situations where we have some fluid commodity in the network. It can be information, it can be traffic, it can be anything. So we have, once again, so those are network flow games. We have a flow network. So this is given by the set of vertices, the set of edges, the capacities of the edges, and the source node and the target node. And its associated network flow gain would be collisional gain and V, where the agents are represented by edges, and the value of each collision is the value of the maximal flow that those edges can pass through them, right? So for each subset of edges, the value of C is given by the value of the maximum flow F, when we only consider the edges in C. So we assume that F of E for each E outside of our collision is 0. There's also, so that's obviously a monotone game. The larger set of edges we have, the more flow we can send to those edges. So that's a monotone game. And there exists a so-called threshold version of this game, which is a simple game. So sometimes we are not interested in the actual amount of flow that we can send, but we only are interested whether the subset of edges can carry a flow of K or not, right? And then the threshold network flow game is a simple game. Where the value of collision C is 1 if there exists a flow F such that F of E is 0 for all those which are not in C, and the value of F is greater or equal than, let's call it T, which is a given threshold. And it's 0 otherwise. Some more problems related to security, but in a different situation. Imagine that we have adversary that travels from the source node S to the target node T, and the agents cooperate in order to stop the adversary, to disrupt all the paths from S to T. So we would have a game where the agents would control nodes in the graph. So each agent controls a node. Okay. And the agents form coalitions. So a coalition would be a winning coalition if it manages to stop the adversary, that is, to disrupt all the paths from S to T. So that is, a winning coalition would be a coalition that represents a cut between S and T, a vertex cut. Okay. So write it down. A path disruption game is played over the graph. With a source node S and target node T. A coalition C wins, and in this case it will have the value of 1 if removal of the vertices controlled by this coalition disconnects C from T. There may be several paths from S to T, so we have to disconnect all of them. Right? So that means that every path from S to T passes through some node in C. So in this case, C is called a vertex ST cut. Cut between these two. And we would say that the value of C is 1 if C is a vertex ST cut, and it is 0 otherwise. Some other domains where cooperative games are used are in actually multiple agents trying to solve different tasks. And in some situations, in crowdsourcing environments, in labor markets, and so on, we may assign the same task to multiple agents, to more than one agent, because either agents may fail to complete the task to a satisfactory level, or actually if we have many agents and all of them, some of them to complete the task, then we can just increase the quality of the solution by having many agents. But in those situations, it's not easy to incentivize the agents to compete for the same task, right? So they would expect probably some ex ante guarantee of a payoff given their abilities, given their skills. Right? And this can be, such a situation can be modeled as a cooperative game where for a subset of players, its value would be for us the maximal level of ability to solve the task. And then we can compute third division, for instance, of the payoff, Shapley value, to give them some guarantees of the payoff to incentivize them to compete for our tasks. Right. So we have it's called a cooperative marks game, where we have a set of agents and vector of weights. So this is set of agents. This is vector of weights, where those weights represent the abilities of the agents to solve the task. So those are ability levels. And then the value of a given coalition C would be the maximum over all members of C of this weight W. By any coalition. There is a more general model that deals with similar situations where we have agents with different skills, and now we may have also different tasks that require different set of skills. Those are called coalitional skill games. So we have the set of agents, and agents, we have the set of tasks, tasks, and we have some supersets of skills, say K of them. Now each agent has some subset of skills, say S of AI, which is a subset of S. Those are skills that agent AI has. Now each task requires some subset of skills. So S of TJ, also a subset of S, would be skills that task TJ requires. Now, given a coalition of agents, C, we would say that C performs some task Tj. If C has the skills that Tj requires, that means that, let's call it S of C, which is the union of those sets, right? Those are skills that each member of the coalition has for AI in C. So this set should contain the set of skills that T requires. Let me denote it as the fact that C can perform some task Tj, we denote it by, say, B, C, Tj. And then tasks that C can conform. Those are all the tasks that C can perform. And the value of each coalition is given by the function that corresponds, that maps each subset of tasks to a real value, right? So this actually the value of C, let me use another letter here, say U. So this is the task valuation function that for each subset of tasks says us how much that values for us, and the value of the coalition would be U of T of C. So that's the set of coalitions that our coalition performs, and we map that to a real value. That would be the value of the coalition. To those games we also can define a threshold version, which would be a simple game. For instance, if we have only one task, that requires the set as prime of skills, then the value of C would be 1 if the set of skills that C has contains as prime, right? So it can form of all the tasks, and 0 otherwise. So those are examples of cooperative games. They're not all of them, there are many, but I've just chosen something which appeared in last years due to different domains. There are also 2 big classes of cooperative games that we are not going to talk about in this course, but just so you know they exist. One is cooperative games with overlapping coalitions. In all those games, we only consider situations when an agent is a member of a coalition as a whole, right? But we can look at situations where an agent distributes his time between different projects he works on, right? And that would define overlapping coalitions. There are also games which are called hedonic games. Those are games where we do not give values to coalitions, but each agent has some ordinal preference about different coalitions of partners he can be together in a coalition. So that would be a subclass of non-transferable utility games, actually. We spoke about them a little bit. And another question which is also of interest to this part of research is optimal coalition structure generation, the one that we mentioned before. Now, today you are getting your homework assignment. Next week, Enrico will be here, so I only see you after the Easter break. I will complete the lecture notes that I still owe you on the website. They will be there. What else? Submission of the homework. You can either, so the first homework assignment is for 2 weeks, so you need to submit it on the 12th of March. You can either bring it to the class if it's ready in the morning. morning, but I would accept submissions until midnight, so you can send me a scan, but the scan should be readable. If it is not, then it is your and not my fault. And if you send those by emails, please send to my ECS address, not to the university address. I will find eventually those sent to the university address. It's not as fast because there is some problems with transferring those emails. I always lose some. Any questions at all? Okay, then happy holidays, and I see you in a month. Or 2 actually.